I may mention that G and information about G can be related to positions on a phase diagram, and that's what we're going to talk about now. We're going to ask ourselves the question, well, where is G on a phase diagram? Like, where is the information associated with Gibbs energy? Again, I know I mentioned it before, but one more time to stress, the reason Gibbs energy becomes important is that we're dealing with a pressure temperature dependence here. So if I take a look at one spot on a phase diagram and I do an experiment at a constant pressure and at a certain temperature, okay, there's a certain phase that shows up for that isobaric and isothermal experiment. Now we know from our last discussion that, all right, there's a solid phase that would result if I had that pure species in a closed system at this point, all right? So that means that somewhere along the way, because G maps onto the second law for isobaric isothermal situations, right? Because it maps onto the second law for those situations, right? G information is dictating that the solid phase is favored here, okay? So the G information is directing spontaneity again because we have the correct conditions for it to do so. Now, what's this idea of chemical potential? Well, remember that this is a classical theory, and so I just want to kind of remind you, we looked and we made arguments associated with potentials before, and you can even kind of think about like a ball rolling down a hill, all right? So chemical potential ends up being this mathematical framework that we build for G. Chemical potential and G, they contain the same bits of information. Why we're recasting it, and let's just say that this is some kind of distance here, is because from a classical theory, we understand that balls like to roll down hills, that low potential energy situations are generally favored, all right? And that's the idea. Lower potentials are favored. And so we kind of build a lot of arguments in science based off that idea that if we can get to a lower potential energy situation, great, all right? So we define a chemical potential because G, or we define a chemical potential in the context of G, because G kind of follows the same idea. If G is mapping on to the second law because of the conditions of the experiment, what do we know about favorable G's? What do we know about how G directs spontaneity? A G that's lower, and in fact a delta G that's negative, dictates that the process is going to be spontaneous, that the process is favored, right? The more negative you are, the better. And in fact, we saw that if we had a delta G that was positive, we would say that that process was non-spontaneous as written, and in fact, the reverse was spontaneous. So a positive delta G for a process stops it and makes the reverse happen, and a negative delta G, right, means that that process is spontaneous. G follows what a potential does. So we're going to recast G in terms of what's known as a chemical potential, right? Because of this same idea. Lower is better. Lower is better, both for potentials and for G. So essentially, we'll eventually come back to this, but the reason that this is a solid over here, right, based off of this argument, is because the lowest G possible is the G for the solid state. The lowest chemical potential possible at that P and that T, right? The lowest chemical potential is, right, for the solid state, okay? So we're sort of taking our second law ideas now, we're applying it to what we saw on our phase diagrams. So what is a chemical potential? The thing to remember about a chemical potential is it has this mathematical definition. It has actually two kind of equivalent definitions. But the thing to remember about it that's different now is we have to build in the idea that N is no longer fixed. And it's not necessarily that N total isn't fixed, right? So N total might be. You might have a certain sample size, but if we're making those changes on the phase diagram, if we're making a solid into a liquid into a gas, all right? The individual species, like the number of moles of solid and the number of moles of liquid and the number of moles of gas, those will change, okay? So think about even just melting something. You're in the solid state, you're in that part of the phase diagram we just saw. You start to heat it, you turn things into a liquid. These are no longer set, right? And that's a big deal for us because throughout the whole semester, we've kind of been doing problems where we don't really worry about N. We have a sample, nothing's really changing about it. But now if I'm talking about a phase transition between these states, right, even sublimation or deposition, right, these are going to change. So with that in mind, all right, what we do is we think about, okay, let's take, for example, a solid going to a liquid. Let's try to write G for that situation. Well, if I have a G, right, and I'm making this change, and I'm in a situation where I might get some coexistence, the G has a contribution from all of those particles that are liquid. And the G has a contribution from all of those particles that are solid, all right? The number of moles of liquid species are going to contribute to G in the liquid, and the number of moles of solid species are going to contribute to G of the solid, all right? So what we can do now is we can say, okay, let's approach this like we've been doing all semester. What is G a function of? It's a function of P, T, N for the liquid, and N for the solid. And we're doing this for the solid to liquid transition, but again, it is kind of applicable for whatever transition you're looking at, right? So if I write this out, okay, then what I can do is I can write a dg based off of these 4 variables now. So it's going to look like partial G, partial P at a constant T, NL, and NS, dP, plus partial G, partial T at a constant P, NL, NS, dt. And now that sort of looks familiar. We didn't include those n's before because n was just set and it was assumed to be constant. But now our dg is also going to have a plus dg dn liquid, partial G, partial N liquid, at a constant T, P, and N solid, dN liquid, plus partial G, partial N solid, constant T, P, and N liquid, dN solid. So it's this much more complicated expression because now the variability not only is just in the dependent variables P and T, or independent variables P and T, but also in how many actual number of moles you have for your liquid state and how many moles you have for your solid state. Now, when we talk about phase transitions, when we talk about actually doing an experiment associated with a point in a phase diagram, as we said before, we want that important G. So these terms are going to go to 0 because we're going to do things under isobaric conditions and isothermal conditions. So even though it looks complicated to start, we use our keywords for just looking at a point on the phase diagram and deciding, right, which is favored in terms of G. And this is what dg looks like, right? It looks like dg, right? Sorry, it looks like partial G, partial NL, DNL, plus partial G, partial NS, DNS, okay? So these species right here are what we're going to define as our chemical potentials. These are going to dictate, and I'm going to show you mathematically how, all right, whether for this liquid and solid interaction, we get the same amount of liquid and solid, whether we get a favorable liquid state so that things move to that liquid state because of a lower potential energy situation, or whether we get a favorable solid state so things move to that solid state because of its lower chemical potential situation. Chemical potential is given the symbol mu, right? Chemical potential is given the symbol mu. This right here, we're going to call mu for the liquid. So that partial derivative right there, that's mu for the liquid. Let me just circle it. By definition, right? So this is the partial derivative identity for chemical potential. It's dg, dn at a constant Tp and all other n's. That means over here we could rewrite this as mu solid. Right? If I'm calculating dg, right, I still have this d and l, and I still have this d and s to consider. Okay? So now this is cast in terms of chemical potential. So how does chemical potential work to have the lower chemical potential be favored? Well, let's give this situation a chance, right, to exchange liquid and solid particles. All right, just to kind of make you understand where we're at, let's go back to our phase diagram. I'm just going to sketch it really quick. Let's say we're here, but let's say we start with a liquid. Now, we know that we want a solid, but imagine that I introduce at this P and at this T a bunch of liquid. Now, we know it's going to solidify based off our understanding of the phase diagram. But what does chemical potential do to take that liquid and make it a solid? Right? Well, let's understand something. If I have a liquid, right, and this is the change in the number of moles of a liquid, how does that relate to the change in the number of moles of solid? These two should be equal and opposite. If that liquid starts to go away for that one chemical species, what does it turn into? It turns into that solid. Okay, so I'm going to use this substitution here. I'm going to get a dg that looks like a mu L, right, minus dn solid plus mu S dn solid. So now there's only one dn there because as one species changes its form, it goes into the other species. So let's rearrange this and let's write our final expression that we can analyze. dg looks like mu L, the chemical potential for the liquid, all right, with a negative sign out in front, right, plus mu solid, the chemical potential for the solid, with a positive sign out in front, dn solid, and sometimes it's easier for us inside here to rearrange this so that it looks like a subtraction. So again, what we have now is an experiment where we can calculate a dg. Now, we know what dg has to be for us to have a spontaneous situation. dg has to be negative. So let's look at a couple different situations. Let's give ourselves a couple different conditions and talk about how chemical potential works and how a lower chemical potential is better or dictates flow. So we know spontaneity for dg is negative, right? So over here now we have to ask ourselves the situations that lead us to getting a negative value for dg over here. Well, let's go ahead and say that for this first instance that this right here gives me a negative number, this subtraction, okay? So this subtraction, if it would give me a negative number, means that, okay, if the overall process is negative and spontaneous, then dn solid has to be positive, okay? So what we did is we just assumed that inside here we get a negative value, okay? Well, if this subtraction gives us a negative value, what does that mean? Inside here, the only way to get a negative value, right, is if mu liquid, okay, mu liquid is greater than mu solid, okay? Now think about what happens here. If mu liquid is greater than mu solid, you get this negative sign. But to make the overall situation have a negative dg, dn solid has to increase. So really try to digest this. This is pretty powerful and important. There's a lower chemical potential for the solid. And what happened to that state that we made? If there was a lower chemical potential for the solid, what happens to that experimental setup? Lower potential energy for the solid, more moles of the solid resulted, right? The lower potential dictated how the system behaved. It told me that we were going to get more solid out in the end, that the solid side was favored because it's at the lower chemical potential, all right? Let's take a look at the other observation that we could make here. What if we prepared a situation in a different part of the phase diagram? And we analyzed that part of the phase diagram, and what we found was this subtraction here was positive. Well, if we're going to get a spontaneous process, what that tells me is that in this situation where this subtraction is positive, dN for the solid would have to be negative. So the solid in this instance, set up where this is positive, would go away. You would lose moles of solid. So if that's the case here, right, what's the only way to get a positive value inside there? Well, mu of the solid now, right, must be greater than mu of the liquid. Okay, so what happened? The liquid chemical potential was at a lower value. And what did we see? We saw that the solid went away. Well, where did it go? Remember that dN for the liquid is equal and opposite dN for the solid. Oh, so this dictated to the flow to make more liquid, right? To make more liquid. So in this instance, dN for the liquid would be positive. So chemical potential behaves to dictate the flow of these different situations. And in this case, in the context of phase diagrams, it dictates what state you'll see for a given P and T. The lower the chemical potential, the better. Now, we can kind of take a look at this through another lens. Right? And I just want to point this out. This is like an alternate definition. Of mu. Remember what we just shown? We show that partial G, partial N at a constant T and P and all other N's, right? That was what we defined as our mu. And this is true. But you can observe here, well, if I want to actually carry out this partial derivative, if G looks like N mu, and I substitute it in there, right? Partial N mu, partial N, at a constant T and P. Well, hold on a second. Mu can come out, dN, right? Gives me a 1, and I get mu equals mu. Okay? So this is a formal definition of mu, and it works, and we just showed how it worked. But this gives us perhaps a little bit more insight into directly what mu is relative to G. Essentially what it is mu is G over N, right? Mu is G over N. So another way that we describe mu is we actually describe it as a molar Gibbs energy. So when do you use one definition for another? Based off of whatever suits you. If we have this partial derivative identity, we have to make sure we identify that it's a mu. But we can also use this simple identity that mu is essentially a molar Gibbs energy. The behavior doesn't change relative to this definition or this definition. It's still the same mu. The lower the better. It still works. Okay. The reason that we introduce this, though, is because when we get to equilibrium, sometimes it's beneficial to see the partial derivative identity. Sometimes it's better to see the more standard molar Gibbs energy definition, right? But let's go ahead and let's make a plot here of mu versus temperature. So let's kind of think about what happens in a phase diagram, and let's kind of tie everything together now. So, right, let's set a given P for our phase diagram, and let's go ahead and talk about this process right here, where we walk across and we do a series of experiments with a set P at this temperature, a set P at this temperature, a set P at this temperature, over and over again. And we map out what must happen, all right, at each one of these points along the way. So we know from our understanding of phase diagrams that the process will take us from a solid to a liquid to a gas. So what must be happening to the chemical potential as you go through that situation, right? Well, if we take a look at G information and how we understand the behavior of G in this situation, then we'll also understand how mu behaves. So, for instance, from last chapter, we derived that partial G, partial T at a constant P is something that we know to be minus S, right? Now, how does that apply here? What are we doing? We're keeping pressure constant as we walk across. What's changing? T is changing as we walk across this process. And what do we want to monitor? We want to monitor what happens to G. Well, what happens if I make this a molar G? And what happens if I make this a molar S to keep the equivalence? Well, this species right here, whenever you see a molar G, you can replace it with mu. So chemical potential changes as molar G changes because they're the same thing, right? But the change that's important here is that the change of that Gibbs energy, the change of the chemical potential, it depends on minus S, minus the entropy, okay? So keep this in mind. This is what we're talking about, all right? And now let's go and let's try to look at making a plot of mu versus T, okay? I'm remind us of this. I just want a little bit more room here. So on this axis, I'm going to put mu, right? On this axis, I'm going to put T. T would have units of Kelvin. Mu is a molar Gibbs energy, so it has units of kilojoules per mole, right? So what I'm going to do is I'm going to start by drawing curves, right? And I'm going to draw mu for the solid first, right? So I'm going to make this dashed blue line, right? This is mu for my solid, right? So what happens for mu for my liquid? Well, remember, this kind of mimics what's happening on that phase diagram. We know we go from solid to liquid to gas, right? So mu for my liquid, I'm going to write like this, right? Mu for my liquid, I'm going to write like this. Now, we can kind of see what happens. Where these curves intersect, right? This point where the red and the blue meet. What is that point right there? That's the point where, all right, mu solid equals mu liquid, right? Go back to our expression for dg. We know that if mu solid equals mu liquid, which side is favored? Well, neither is favored. Okay, well, wait a second then. If neither side is favored, remember that subtraction? What you'll get is that dg equals 0. What do we know about dg equals 0? When dg equals 0, we have an equilibrium situation. Well, in the context of our curve, our phase diagram, this right here then, this corresponds to the melting point temperature down here. This is the actual point on the coexistence curve on the phase diagram. So right down here, I'm just going to draw it real quick to make sure you understand. All right. So we're walking across this P and this T phase diagram, and we're doing a series of experiments, and we're coming here, and oh yeah, this right here, this low temperature region, which potential is lower? Mu solid, right? So this red line, remember, is mu liquid. Okay? So mu solid is lower than mu liquid over in this region. And what do we see in our phase diagram? We see a solid phase. This point right here corresponds to this point there. This is where they're in equilibrium. This is the coexistence region. This is where the potentials must be the same. We're getting equilibrium, which corresponds to dg equals 0, right? Oh yeah, this corresponds just like this does to the melting point, okay? And we can do the same thing for the gas. Now, I'm only going to draw it in one part here. So you can imagine the gas, right? Mu versus T looks like this. So then if this is mu for our gas, okay, then this point right here, that must be our boiling point. That must be our boiling temperature. That is walking out here and finding this. What about this region in between? This region in between, we know that's our liquid state. What's the lowest potential, chemical potential in that situation? It's the red, which is our liquid, all right? And what we're left with here is from this point on, what's the lowest potential for a temperature? Because this kind of extends all the way down here. The lowest potential from that point on is going to be a gas. So the potential dictates, all right? The lower the potential dictates what state you're going to see. So please make sure you can make this link as we walk across a phase diagram. What's happening is the chemical potentials are getting lower and lower and lower for those states, all right? So I'm just going to redraw this one time to show what's actually happening without multiple curves there. And hopefully it solidifies the ideas. As always, make sure you're taking notes, you're reading, you're writing down questions to ask me. So this diagram, without all that extra information, so what we're going to draw here is the chemical potential for the system. All right, so not the chemical potential of all species over all temperatures, because we know up until the melting point, there's the lowest potential energy that dictates, lowest chemical potential that dictates the behavior of the system, and that's mu for the solid. But then we see that it changes, right, after the melting point to the boiling point, and the lowest chemical potential is the chemical potential of the liquid. And now after the boiling point, the lowest potential energy, the lowest chemical potential is the chemical potential of the gas. So if you look at the last diagram that we drew, this is just taking the lowest one, right? So this is what the system is actually doing. Wait a second, what do you see happen after a phase change? So here's our melting point, here's our boiling point. After a phase change, we get a more steep slope. So as a chemical potential takes over for the previous chemical potential, we see a change in slope. Now this makes complete sense, and this is the final linking that I'm going to do. When you go back and you think about this expression that we had earlier, right? Remember we made it molar, and so this was how mu changes with T at a constant P, right? What happens when you go to a solid to a liquid? When you go from a solid to a liquid, you get more disorder. What does this tell us? The slope of a line of mu and T, dg dt, right? This is all done at a constant P. The slope will change based off of the disorder, and the slope becomes more negative, okay? So as you make a phase change, here's solid, and it has a pretty low entropy, so it has a pretty low slope here on this diagram, all right? Because remember, this is how mu is changing, because G bar is mu. So it's a pretty low slope because it has a pretty low disorder. As soon as you go from a solid to a liquid, what has changed? You now have more disorder, so you have a much more steeper slope. What about going from a liquid to a gas? More disorder and a more steep slope, even further than the difference in slope between the solid part and the liquid part. So this natural variable relationship and G's behavior, it ties directly to chemical potential, and it ties directly into what you see in a phase diagram, right? A lot to digest here. Rewatch this video, take good notes. As always, please ask me questions.